Now it is time to take longer strides.
Achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth.
The Eagle has landed. It's one small step for man, one giant leap for mankind. 1201, rocket 1201 alarm.
Time for a great new American enterprise. Time for this nation to take a clearly leading role in space achievement, which in many ways may hold the key to our future on Earth.
I believe we can send humans to orbit, Mars, and return them safely to Earth.
Hello and welcome to NASA's Headline News, your weekly update featuring events and activities from NASA Education. I'm Kurt Hogan. I'll be here every week updating you on the weekly activities, events, and happenings around the agency. In an effort to increase STEM education and learning amongst teens, NASA's getting on board with the video game industry. The video game is called Moonbase Alpha, and you're seeing stills of it here before its worldwide release. As a player, you step into the role of an exploration team member in this futuristic 3D settlement on the moon. Your mission is to restore critical systems and oxygen flow after a nearby meteor strike cripples your solar array and life support equipment. The video game allows for single or multiple players. The game is designed to show how NASA content can be combined with a cutting-edge game engine to produce an experience that inspires interest in science, technology, engineering, and math, skills critical to achieving NASA's exploration goals. NASA's scheduled release of the game is July 6th on the Valve Stream network. Looks like a lot of fun and educational. For more information about the Moonbase Alpha game, visit www.nasa.gov/Moonbase Alpha. Well, some students may think they're good at designing homes, but how about designing homes for use in space? Well, here's their chance to see if they've got the right stuff. NASA's challenging college students to design concepts for inflatable habitat lofts for the next generation of space explorers. The winning concepts could be used in the exploration habitats of the future. The XHAB competition is a university-level challenge designed to encourage further studies in spaceflight, related engineering, as well as architecture. This competition requires students to develop space habitats while also helping NASA gather new and innovative ideas for its current research and development. Students will design and actually build an inflatable loft that will be integrated into NASA's operational prototype lab unit. The competition winner will participate in a demonstration of his or her design during a field test next summer. And for information about this competition and registration requirements, visit www.spacegrant.org/XHAB. Well, successful pre-service teacher institutes have just wrapped up at 2 NASA centers. Minority and underserved college students spent 2 weeks at Marshall Space Flight Center and Ames Research Center, learning how to be better STEM educators. The students were immersed in NASA resources through inquiry-based learning. They also participated in workshops where they learned how to develop and teach space-related science, technology, engineering, and math lessons to 4th through 7th graders. And finally this week, teachers in Houston are getting trained on building rockets to help their students reach for the stars. 2 education specialists from Marshall Space Flight Center will travel to Houston and partner with the Johnson Space Center to teach a basics of rocketry workshop at the agency's Educator Resource Center. The workshop will be attended by K through 12th grade students and informal educators. The educators will build several model rockets and learn how to safely launch them. Additionally, several rocket-related activities from NASA's educator guides will be demonstrated for the teachers to use in their classrooms and enhance their own lesson plans. Well, thanks so much for joining us today, and be sure to check back often for the very latest in what's happening with NASA education. For all of us here at Headline News, I'm Kurt Hogan. Stay tuned following the broadcast for more events right here on the NASA DLN Info channel. Until next time, we'll see you later.
space project in this period will be more impressive to mankind or more important for the long-range exploration of space, and none will be so difficult or expensive to accomplish.
What we're looking for is not just to continue on the same path, we want to leap into the future.
Okay, we're go. Altitude 1600.
Hello and welcome to the Summer of Innovation webcast. I'm your host, Kurt Hogan, coming to you from NASA Langley here in Hampton, Virginia. You know, every single week we've got an exciting web series for you, an exciting webcast for you. We've got one at 11 o'clock a.m. and we've also on Tuesdays and also at 4 p.m. on Thursdays. That's Eastern Standard Time. And we're going to take you to a different NASA center, or at one of our various NASA centers around the country, and one of our NASA experts will teach you something really exciting dealing with STEM education, which of course is science, technology, engineering, and math. And one of those experts will pick one of the 6 topics which you see on the board behind me. We've got Mother Earth, Father Sky, life sciences, universe, aeronautics, my favorite, rocketry, and also robotics. So stick around for that. Today we've got something very exciting for you with my favorite topic, which is robotics. We are going to take you to the Stennis Space Center in Mississippi, where Kelly Witherspoon, who is the Instructional Technology Coordinator, is standing by to tell you all about today's webcast. Kelly, how are you?
Oh, we're just fine. Kurt, how are you?
I'm very good. Hey, you might want to remind folks, too, that they can log on and ask you questions during the webcast.
All right. Well, my name's Kelly Witherspoon. I want to welcome you here to Stennis Space Center. And today I have with me Christine Powell. She works at the E-Complex, which we'll learn a bit more today. But as we go through the program, we're going to learn about rocketry, which is the main line of business here at Stennis Space Center. We've been testing rocket engines at Stennis since the early 1960s, all the way up to today. We've gone through a series of different programs. We started with the Apollo program, testing the first and second stage rockets here at Stennis Space Center. Then moved into a new line of business, testing all the Space Shuttle main engines here at Stennis. And as we move forward into the years to come, we'll be testing other types of rockets in order to take us into brighter and more future destinations for NASA. But as you hear the program today, students, if you'd like to ask a question, we'd like for you to go to and send an email to nasalearn@gmail.com, and so that's NASA, NASA, learn, LEARN, @gmail.com. So if you come up with questions and stuff and you would like to ask Christina or myself, towards the end of the program today, we'll take all your questions and be able to hopefully be able to answer them. But I'm going to send it over to Christine, and she's going to talk today about rocketry and what she does here at Stennis.
Well, thank you, Kelly. Good afternoon, everyone, and welcome to Stennis Space Center in South Mississippi. Yes, today we are going to be talking about rocket propulsion. And just to give you a little idea about the topics that we'll be discussing, we'll look a little bit about what Stennis Space Center does. We'll talk a little bit about a certain law of physics called Newton's third law, but don't get worried, we're not going to get too complicated or detailed. And we'll talk a little bit about how that applies to propulsion and specifically to rocket propulsion. We'll talk a little bit about some different types of rocket motors that we have experience with, and then we'll give you sort of a day in the life of a Space Shuttle main engine and the certification testing that each engine has to go through at Stennis before it's allowed to go down to the Kennedy Space Center and be installed on the Space Shuttle for a launch.
We also have a cryogenic presentation at the end. So this is something that's really unique. I think if you've never watched before how you can freeze things due to cryogenics, and Christine will tell us more about that as it relates to rocketry. But we have that in the program today as well.
Absolutely, and we're going to have a lot of fun with it. Okay, so let's get right into it. This is a picture of the test complex here at Stennis Space Center, and you can see some very large structures in the background, what look like large buildings. And those are the test facilities where we actually test the different engines or parts of engines that different companies can bring to us. So if a company is coming up with a new design, they might want to come test it out here before they start building a bunch of them to sort of work out any kinks that they might have. Or once they build them, they might want to bring them here so that they can certify them before they actually install them on a rocket or a vehicle to launch.
You know, it's really interesting. I've been at Stennis for 11 years now, and we have 3 test stands out in the test stand area. We have 2 smaller stands. They're called the A1 and A2, and we have a very large B stand, and it's a double. It's really weird how you can test 2 engines at once. But that one is large enough that you can see New Orleans from the top of it. It's on a clear day. New Orleans is about 35 miles from here, and you can see New Orleans from the top of the B stand. It is the largest one we have. And we just finished construction, or are we still working on that new test stand out there?
We're actually still working on the brand new test stand to do some altitude simulation testing.
That was the most interesting part when I started reading about the new test stand. It said it will simulate being in outer space. Now,
well, it's not quite outer space, but almost outer space.
Almost outer space.
Right.
So different from the space shuttle whenever we used the throttle on it, which was just high altitude, but it's going to be even higher than that?
Right. We're going to simulate a very high altitude. A lot of rockets that launch, they have the engine that starts off at the ground, and that's a sea level engine. That's usually called the first stage. And when the rocket gets way up in the atmosphere, oftentimes that first stage drops off and the upper stage engine kicks on.
Oh, okay.
And so it's the upper stage engines that we can put into the special test area, and we can pull up, vacuum down on it, and represent a really high altitude so that we can make sure that it really starts where there's maybe not so much air to help the combustion process.
Because that was the part I wasn't quite grasping. Now I really understand what they're going to be doing out there.
Oh yeah, it's going to be really exciting.
Now the test stands were built back in the early 1960s. They tested the first stage rocket on the B stands and tested the second stage rockets on the A1 and A2, from what I understand. And the process has not changed very much since the early 1960s as far as the 3 stands go.
Well, as a matter of fact, it seems like as much as we change, we stay the same.
Yeah.
You know, we come up with great ideas, new technology, new materials to make these rockets and motors out of, but when you get right down to it, you really need to test it to make sure it's going to work before you risk putting a vehicle or a human life on top of it to launch, because you want to really make sure this thing's going to work before you put it in that environment.
You know, I had one of the past NASA directors once give a scenario, and he said it's like placing a delicate lamp on top of a nightstand. And he said, so imagine the lamp being the engine. And in the very beginning, it's right on the edge. So the lamp's here and it's teetering right on the edge. And it could fall off and break, which would be a bad thing. And so the engine could fail, and that would be a bad thing. But through a series of testing, it keeps moving closer and closer to the center of the table. And then eventually you have it right in the center where it can't fall off or it technically won't break.
Right. We basically run these engines through all sorts of different scenarios and try to test different conditions so we really know that these things will work when we need them, how we need them to work.
And as far as I know, we've never had a space shuttle main engine failure.
That's right. Every one of them has been flight certified here at Stennis, and every one of them has performed wonderfully when launched.
Oh, that's fantastic. Yep. Well, let's move on with our show and so we can tell them some more things.
Okay, great. Okay, the next thing we're going to talk about is a law called Newton's third law. Some of you may have heard about it. Basically, it says for every action or force, there's an equal, opposite, and simultaneous reaction or force. And for us, propulsion is the force that creates, it's the force that drives the rocket off the ground away from the Earth's surface. So let's take that into practical. Okay? If I'm going to exert a force on you, you have 2 choices here. You can either fall away in opposite reaction, or you can push opposite against me so that you're standing still, but it all happens
Okay.
simultaneously.
All right. That
Okay.
makes sense.
So
Okay.
if we want the rocket to launch up off the ground, we have to create a force greater than the mass and the weight of the rocket so that we can get it up off of the surface of the Earth away from gravity.
So looking at the space shuttle, it has two different types of rockets. We have a solid rocket and we have a liquid engine rocket.
Right?
And so we have to create enough force to push down on the ground to lift the mass of the whole shuttle up into space. Is that what we're referring to?
Basically, yeah.
Okay.
That's pretty much it.
Interesting.
So Newton's third law is not so complicated, right?
No, not really.
No? Okay.
Yeah, really good.
And just another example of propulsion, just something kind of interesting to think about, is a squid uses jet propulsion. But instead of using a fuel, it sucks in water from the ocean around it, and it forces that water out of a funnel in a jet stream in the opposite direction that it wants to go.
So can it shoot forward and make it go backwards?
Yes, it can. It can shoot
how
left
cool.
to go right, and it can really control its direction, how quickly it moves, based on how much water it brings in and how much water it shoots out.
You know, I've been here a long time. I've never heard that analogy.
Yep.
That's a great way to explain it.
It's kind of a fun concept to think about a squid being a jet. So, okay. Now for rocket propulsion, some of the terms that people use, or some of the words that they used, are thrust and mass and nozzle. And basically all that's saying is that a rocket creates this propulsive force, this thrust, because of the mass escaping through an exhaust nozzle. So this nozzle, which is usually towards the back where the motor is, has this, what you see, the flame coming out the back, this massive thrust happening, and that's what causes the rocket to lift up off of the ground.
So technically what you're saying is that the nozzle or the cone, the part that we see, is the part where the flame comes out and it directs that force downward?
Right, it kind of controls
Okay.
the direction. I don't know if people have ever watched it before or seen a picture of it or in the movie, but the space shuttle main engines can actually do what we call gimbal. They can actually rotate a little bit. That kind of helps a little bit of the turning and maneuvering, in addition to some of the other little thrusters that they have installed.
Kind of like steering a car?
Kind of, yeah.
Oh, okay.
Kind of. A little bit more complicated, but kind of.
I was just wondering. It seemed kind of cool.
Yeah. Okay. So, a lot of the motors and rockets that we talk about within NASA, there's so many different types, but we're going to really talk about three kinds today. There's solid rocket motors, liquid engines, and then hybrids. And if you think about a solid, it's kind of like a firecracker. So once you start the fuse, it kind of lights, and the powder or the fuel inside of it will burn until it's all exhausted. And so you really don't want to light it unless you want it to burn, and you can't stop it and start it back up again. So it's very powerful, but there's some issues with working with solids. So they are great in certain applications, and then in others maybe you want to use something different.
I think of a Roman candle when I think of the solid rocket boosters on the shuttle. And that when you light a Roman candle, it's going to burn from end to end. You can't stop it unless you throw it in a bucket of water.
Yeah.
But it's going to run indefinitely until all the fuel is spent out of it.
Right, and if you look at the space shuttle stack up that we have here, the white boosters that you see on either side of it, those are solid rocket boosters. So the fuel inside of them is a solid. And if you ever watch a space shuttle launch, you'll notice that they're the last things that get lit because you want to make sure everything else is working before you start them.
And just like a Roman candle, once you light it, I understand
You're going.
it's going whether they want it to or not.
That's right.
So, and then you mentioned liquid.
Absolutely.
So-
Okay, so let's look at liquids.
All right.
Okay, so think about your family car or the bus that you maybe ride to school in every day. The liquid fuel inside of it is gasoline. But the cool thing about it is you can stop it, turn it off, restart it. You can make it go faster or slower depending on how far you push the gas pedal and how much you let off of it. And so the space shuttle main engines that are at the bottom of the space shuttle, there's 3 of them, they're liquid engines. But instead of using gasoline like you get at a gas station, they actually use a cryogenic liquid oxygen and liquid hydrogen, which is what is in this really large external fuel tank.
You know, I always tell my students, Christine, that it's 500,000 gallons of liquid hydrogen and oxygen. It's 2/3, 1/3. 2/3 hydrogen, 1/3 oxygen. So can you imagine that you had to fill this up at the gas station before you got ready to go? How long it would take to pump 500,000 gallons of gas into it before you went up into space?
It would take a really long time.
I just can't imagine. And I know that it takes them a really long time to actually get the liquid hydrogen and oxygen inside of the tank.
Right. They have special pipes that come into the tank and fill the oxygen and the hydrogen. And they have insulation in certain areas, and they have to be very careful. They can only transfer a certain amount at a time. They don't want it to go too fast and introduce too much heat into the system. They have to monitor it and make sure there's no leaks. And because this liquid is so cold, you have to make sure you're using special types of metals and materials so that it doesn't crack and break.
Interesting. And you know, they make these tanks right outside of New Orleans, about 20 miles from here.
Right, and at the Michoud Assembly Facility.
It is true,
right?
yeah. Been there several times.
Okay, so let's talk about a third type of rocket motor. And this is a hybrid rocket motor. And the one that's in this picture is one that we've actually tested here at Stennis Space Center. They can vary in size. They can, be very small with just a few pounds of thrust, up to something that's much stronger than even a space shuttle engine. The good thing about it is the solid fuel that's used is pretty safe in and of itself, and you don't have to worry about it catching on fire or anything like that. As a matter of fact, you have to add oxygen or some sort of oxidizer to it to make it burn. So you can actually make it go faster and slower, kind of like a liquid, just by the amount of oxygen that you give it. And you can stop it and restart it again if you'd like.
Do they have any more thrust than the conventional solid rocket booster or conventional liquid-fueled engines?
Well, it kind of depends on the particular motor that you're looking at. Some of them can be, like I said before, 1,000 pounds of thrust, but some of them can actually be over 600,000 pounds of thrust.
Oh, my land.
So if you think about it, the Space Shuttle main engine can exert a little less than or about 400,000 pounds of thrust. That's like 400,000 pounds pushing down against the
That's
air.
a lot of cars.
That's a lot of cars. Yeah. The solid rocket boosters, they have just under 3 million pounds of thrust.
Golly.
So that's a little over 7 million pounds of thrust to get the weight and the mass of the orbiter with the crew and all the equipment, and the solid rocket boosters with all of the solid fuel inside of them, and the external fuel tank and all of its fuel up off the ground and into orbit.
So we have 400, yeah, I was right the first time.
That's right.
400,000 per engine, so that's times 3, which is 1.2 roughly. And then another 6 million, because it's 3 million, 3 million. So we're looking at, so it has to lift about 7 million foot-pounds is what, to lift all this off the ground.
That's right. And so they have to be very careful with everything that they're going to take with them to weigh it and find out how much it does weigh and how much space it takes up, because they only have a certain amount of cargo room on the shuttle.
What if they wanted to take a piece of paper?
Well, they have certain limitations where the astronauts and the crews actually are able to take a certain amount of things that they want to take with them.
Okay,
as well.
I was just wondering, because
they can take paper.
That's a lot of thrust in order to lift something into space.
Right.
That one piece of paper might bump them over the edge.
Well, they try not to get that close to the margin, is what they call it. So, but that's okay. Okay, so we're going to take some look at some pictures of a space shuttle main engine and how it is processed here at Stennis. Now, we have officially tested the last scheduled space shuttle main engine, but if there was an issue, there may be plans to do something in the future with them. But this is just an example of what most engines go through when they come to Stennis. And there's a lot of people involved in this whole big process to make sure these engines are qualified to be launched.
What's that big crate-looking thing on the screen?
Well, the big white container is the special cargo container that these engines can come in. And they can come in all different types. Depends on the company and what sort of equipment they have and how large the engine is. But a lot of them have special instruments on them so that when they arrive at their destination, people can know whether they were vibrated too much, if there was a lot of bumps on the road. Some of the information or the equipment inside might be very sensitive, so there's special handling techniques, special equipment that has to be used.
So they go over land. They don't go over the ocean like they did before.
Well, it's my understanding that most of the engines that we have received here have actually come over land in
Oh, how
trucks.
interesting. I didn't know that.
Some things that we receive here at the site do come in by barge, but most of what we receive has come in by truck.
Okay, cool.
Yep.
I learned something new today.
Okay, so after the Space Shuttle main engine is inspected, certain things are connected to it, and everything's ready to go, they actually take it by truck out to the test stand, and it's really fun to watch because everybody has to pull over and stay clear of it so they don't accidentally run the truck off the road or anything crazy like that. But the engine goes all the way out to the test stand where a crane lifts it high into the air and actually takes it off the truck all the way up to the engine deck on the test facility so that it can be mounted into the system.
Now, let me see if I can't show them that on this picture. So we have the engine being lifted by the crane,
Right.
and it's lifted up, and I've watched them do this, and this whole deck right here slides out and enabling them to get the engine into place, and then it slides back in.
They actually can put it on a special cart that rolls it into position, and then it can be lifted up so that it's actually tightened up into the test facility, because when we fire this thing, there's 400,000 pounds of thrust coming down. We don't want this engine to go anywhere because we're just testing it. So we have to bolt it down really tight and make sure that it stays in the test stand.
And this is a good picture to show the students too, because here in a second, when we could probably already talk about it, is that you can see the flame bucket. This piece right here that kind of looks like it's in a letter J shape, believe it or not, students, it goes up here where the engine nozzle sticks down, and it is the letter J going down and out into the flame bucket itself where all of the water goes. And we'll talk about that here in just a second, I think, but I want to make sure that I pointed that out. That's a great picture to show you.
Right. And so once the engine is installed, we still have to check it out, make sure that everything's connected right. We have special instruments that tell us how hot different parts of it are, how much pressure different parts of it are seeing, how much vibration, and how much thrust, so that we make sure that it's operating just like it's supposed to be.
Oh, okay.
And then once we are ready, we have these special barges that are huge that bring the liquid oxygen and liquid hydrogen from our cryogenic storage area through a canal system to the test facility, because we just can't truck that much commodity over to the test stand when we need it.
So, students, imagine this. When they built Stennis, they dug these big canals, these rivers that run all across the site, and they bring the cryogenics inside of a container. All of you have seen at one time or another a gasoline vehicle going down the road, or you've seen a big milk container going down the road, that big silver tank driving on an 18-wheeler. That's nothing. These things are huge. You could probably sit 3 of the gasoline containers inside of this container that goes out to the test stand. And they carry on them the liquid hydrogen and...
Or the liquid oxygen.
Or the liquid oxygen. But there's one that does, it's the nitrogen or the helium that they don't carry on it.
No, the nitrogen and helium, we actually have tanker trucks that drive onto the site and deliver it where it's needed.
Yeah, but the 2 key components for getting the space shuttle off the ground, liquid hydrogen, liquid oxygen, 500,000 gallons to get it into space, but that's 3 engines, so it's 1/3 less, I guess, when we do a test.
Right, because we try to test for the full flight duration that an engine would actually see, just to make sure that the full flight profile can be supported. So this engine actually goes through certification process where we pretend that the test facility is the space shuttle and this engine is hooked up, and we're going to see if it can perform for the whole flight.
One of the most amazing things that I have seen and witnessed here at Stennis are the engine tests. Now, when you go down to Kennedy and you watch a space shuttle launch, in about 30 seconds or so, you don't see it anymore. It's gone. It's out of sight. But here at Stennis, our engines are bolted down to the test stand, and they run for the 8.5 minutes. So just imagine all that thrust coming down for 8.5 minutes. The ground starts to shake. You can feel it shaking your lungs. You can feel it shaking your entire body, and your head is extremely loud. And we're a couple of football fields away just watching it, and you have to scream at someone in order for them to hear what you're saying. It's so loud.
Well, the interesting thing is on certain days when the clouds are really low and the sound vibrates more back and forth between the clouds and the earth, it's even louder. And there's actually been recorded instances where a seismic instrument over Mobile, Alabama has picked up the vibrations from
it said it's an earthquake.
Yeah.
I know, it's really weird.
Okay. So this is just a picture of the beginning of a test. And as Kelly was mentioning, if you look at the orange flame, that's where the nozzle of the engine is pointing down into that flame bucket. And we actually pour thousands and thousands of gallons of water down this bucket to keep the bucket cool and to sort of absorb some of that sound vibration that's happening when the engine tests.
You know, students, I showed you the picture just a few minutes ago about the letter J. And so it goes down and it makes this letter J. And if you're looking at it and you're trying to envision in your mind, imagine that there's this big, huge bucket. It's made out of steel. And it's big enough that you could drive several trucks up inside of it, side by side. It's that kind of big. And it has millions of little holes drilled in it. That part always just really amazed me. There's millions of little holes in there, and the flame out of the nozzle starts going straight down. But if we didn't cool it, it would actually burn a hole, from what they told me, straight through. And so they have to add water in order to keep that from happening. But I don't remember how that part works with the holes.
Well, the holes basically form a pattern so that you make sure you get more water in the hotter areas of the deflector and a little bit less on the outside, but that you have the right amount of water in the right part of the deflector when you need it, so that you don't burn a hole and there's not an issue that you have to then go repair your facility before you can test again.
Yeah, the water is amazing. Before the test, they start gushing all this water, and you see the water coming out of the trough. And so water will start coming out of the end of the trough, and it's like a big river. It's like going to one of the water parks, and water's gushing out the end of it. I think it'd be a great ride if we could only patent it.
Yeah, we were trying to figure out how safety would allow us to go in there and play in the
so
water.
The other one was skateboards. It's a great skateboard ramp, too.
Oh, skateboarders would love it, too.
Yeah.
But
So, but then the water starts coming out, the engine fires, flame comes down, and instantly it changes that water into, what do you think, guys? Steam. So the water turns into steam. It's really amazing sight to see.
Absolutely. And here's a picture of that steam coming out. And so as the water, gets heated and turns into steam, this huge cloud forms. And as this cloud gets further and further away from the test stand, it actually cools. And what happens to water vapor when it cools down?
It starts to rain.
It starts to rain. So we've actually had people rained on while they're watching a test, which the kids love because they get to run around in the rain showers.
I always tell people that we create rainstorms at Stennis Space Center.
Among other things. Okay, so I think next we have a video. Oh no, actually we're going to do a little bit more close-up first. I'm sorry. Okay, so here's a close-up of the Space Shuttle engine testing. And if you see how cold it looks, that's because there's these little bitty tubes all around this nozzle, which is that bell-shaped piece of metal hanging down. And all inside of those tubes is liquid hydrogen, which is over 400 degrees below 0 Fahrenheit.
Oh my word, I didn't realize it was that cold.
Yeah, so it actually cools the metal of the nozzle and then gets pumped back up into the engine and used as a fuel. And so that's why it looks so white and so cold while it's firing here.
It reminds me of frost on a windshield during the winter.
Right.
And so the moisture in the air condenses onto the cone itself.
Right, so the humidity and the moisture in the air gets so cold right around that nozzle because there's cryogenic liquid, pumping through these little pieces of metal tubing, and the water in the air just turns to frost and ice.
That's amazing.
Yep. And I think we have a close-up here. When the engine first starts, you see all this white stuff falling off, and it's kind of like when you watch a rocket launch. You see all of these white pieces falling. Everybody's so scared that it's, you know, the launch pad falling apart or the rocket falling apart, and it's not. It's just that frozen moisture that's falling back down because of all the excessive vibration when the launch vehicle goes up.
And it just shakes all that ice right off.
Yep. So if you think about a railing or something that you're going down in the winter and there's ice or frost or something on it and you hit it and it all kinds of falls off, it's kind of the same thing.
Okay.
Okay? And so kind of one of the things that we said before was that one engine alone, and there's 3 of them, but one alone creates about 400,000 pounds of thrust. But the 3 engines together, when it launches, releases as much energy as 23 Hoover dams.
That is a lot of energy, guys.
That's a lot. Okay, and then after we test the engine and we make sure it's all good to go, we lower it back down out of the test stand, and very carefully we package it back up and make sure that it's shipped to Kennedy Space Center. Then there's a great crew at Kennedy that receives these engines, does final inspections, makes sure everything's nice and clean and dry and ready to go. And then in the orbiter processing facility, they actually attach all 3 engines to the back of the orbiter before they go stack it and take it out for launch.
Okay.
Okay? And we're going to see a video in just a second, and one of the things that you'll notice is about 6 seconds before the launch is when the Space Shuttle main engines actually start. And those are the 3 liquids at the bottom, because we really want to make sure that they're all started and that everything is running right before we start those solids.
And so that's 6 seconds right before, and then right when they get ready to launch, they light the solid rockets.
Right, and so what you'll see is there's all these little sparkles looking things happening down here at the base. And all that's doing is it's trying to ignite any excess hydrogen that might be kind of floating around the air down here because of all the chilling and everything that's been happening with the engines. And so right about 6 seconds before the launch, these engines will light and they'll achieve a really good steady performance, and then the solids will light and the shuttle will launch.
Okay. So we have a video?
We do.
All right. Well, let's get that queued up. We'll show the students.
Okay.
And this is the Space Shuttle engine tested here at Stennis. And that's one of our A stands. You can see the letter J. You can see the water coming out. This is a great view because it's at night. And showing it at night, you can really see the flame coming off the engine and where the water vapor or where the water is trying to cool it.
T-minus 10 seconds. Go for main engine start. 7, 6, 5. 3 engines up and burning. 3, 2, 1. And liftoff of Space Shuttle Discovery, beginning America's new journey to the moon, Mars, and beyond. And the vehicle has cleared the tower.
No matter how many times I see that, it always just amazes me looking at the oops. No matter how many times I see that, students, it always amazes me at how well this looks and what we actually do here at Stennis, because at Stennis we test rocket engines, and that is our main line of business. Now, Christine is getting set up to do cryogenics for us. We're going to spend a few minutes taking a look at some of the really unique things that we can do with cryogenics. And remember, the liquid hydrogen and oxygen is what we use in the Space Shuttle main engine, that 500,000 gallons. And that liquid hydrogen and liquid oxygen is what helps propel the shuttle into space. Now remember, if you do have questions, you can email me at nasalearn@gmail.com. That's NASALEARN@gmail.com. So let me get the camera switched over. Are we ready?
Yep, absolutely.
So I'm going to switch the camera over, and she's going to show us a demonstration of how fast this flash is off. So let's take a look at how this looks, and she's going to, let me get zoomed in here a little bit more.
Okay, that's great. So as you can see, I have a special glass container. It's not just regular glass, so it is able to withstand some of the cold temperatures. But liquid nitrogen is what we're using here today, because oxygen and hydrogen are a little less safe because of some flammability issues. But the nitrogen is pretty safe, considering I have special cryogenic gloves on to keep my hands safe so that they don't get frozen. But you can see that the nitrogen is clear, just like water.
And why is it boil?
Well, if you think about it, if I have a cup of water at room temperature, the water is a liquid, right?
Yeah.
But if I put it in a pan and I heat it up and it starts to boil, what happens to it?
It evaporates.
Yeah, it turns up into the steam and it goes into a gas and it's out into the atmosphere.
Okay, that's a good analogy.
Okay, so liquid nitrogen wants to be below 320 degrees Fahrenheit to stay a liquid.
Okay.
And because it's warmer in here than 320 degrees below zero.
Well, I would hope that my lab would not be minus 300 degrees. I think everyone else would think it would be kind of cold.
Well, because it's so warm in here, the nitrogen wants to boil and turn back into a gas. And so that's why we're seeing all the little bubbles and the mist coming off of the cup.
Interesting.
Okay? And in this pan, which is a stainless steel pan, I have some more nitrogen, and you can start to see a little bit of the frosting that's happening on the outside of the pan.
Let me see if I can grab that with the other camera. Yeah, that shows up real well.
Okay, you see how it's kind of white all around here?
Just like on the shuttle nozzle.
Right. That's because the moisture in the air all around this pan is getting so cold that it's turning to frost into ice.
How interesting. It's very similar to what happens to the shuttle engine.
Mm-hmm.
Yeah.
And so if we have air, for instance, hot air balloon rises and goes up.
True.
Okay, the hot air inside, what's happening to all the little molecules that are inside of there?
They're just dancing around so fast they don't know what to do.
That's right. You heat them up, they start going crazy and going faster and spreading further and further apart. Well, what's going to happen if I cool the air inside of this balloon?
Well, the molecules get closer together and they get really slow and sluggish, and it should be very interesting to see what's going to happen.
Okay,
Let's
so
see if I can't do this on the second camera to get a little. There we go.
Okay, so all I'm doing is I'm resting this balloon on top of the nitrogen, and the air inside is getting colder and colder, and so it's, like Kelly was saying, it's getting slower and all the little molecules are getting closer together, and when I pull it out, they're going to warm up. So what do you think is going to happen?
Well, I think the balloon's going to break.
You think it's going to break?
It's going to happen.
Well, I think that the air is going to start moving faster and faster, and the molecules are all going to start warming up and expanding, and the balloon is going to do that too.
That is so interesting. So we haven't destroyed the air inside of it. We just condensed it down to where it was flat.
Right. The air inside got really cold, and actually the moisture inside turned a little bit to ice because as it warmed up, you could hear it cracking inside.
Oh, yeah.
Yeah.
That's true.
Okay, and so now we have our regular balloon back.
How interesting.
It's a little cool to the touch still, but the balloon is actually one of those things that once it warms back up, it's fine. Now, a flower, on the other hand, the tissue on the flower is kind of like the tissue on our skin. So it has some moisture inside of there, and if I dip it in this nitrogen, it's actually going to freeze the petals, and hopefully you'll be able to hear it on the mic, but if not, the petals will become so hard, it's almost like glass, and it'll actually break and fracture.
And that would be the same thing that would happen to
your skin.
Our hand.
Yeah.
We stuck it in there with no glove on it.
Okay, so I'm going to pull this out.
Okay. I can see it really well. Look at that, students. I mean, it's just she's
shattering
just
like
shattering
glass.
it.
Just breaks off real easy. Now in a few minutes, the leafy part will actually warm back up and be fairly normal, but the flowers themselves will start to become more wilted because of the tissue damage. Okay? It's very brittle. And there's actually a lot of different industries that use cryogenics in their processes. The food industry uses it. Health and beauty industries use it. Recycling industries like to use nitrogen to freeze the materials so that they can grind it into a very fine powder and then process it for impurities. It's easier for them to get the impurities out that way and to melt some of the things down. Medical industry, there's a lot of different groups out there that use cryogenic liquids.
Interesting. So not only NASA, but other companies do as well.
Absolutely.
Interesting.
And speaking of food, how would you like a marshmallow?
Oh, I love marshmallows.
You love marshmallows?
I like the s'mores, where you the chocolate, the graham cracker crust.
Where you melt it?
That's one of my favorite ways.
Okay, well, we're not going to melt it today. We're actually going to freeze it.
Aww.
So this is just a regular marshmallow that I got from home.
Mm-hmm.
Bought it from the store. And
Can I still make a s'mores with it?
you can after it warms back up.
Oh, okay. I just wanted to double check.
Marshmallows are one of those things that once they warm back up, they're good to go. You can eat them again.
Oh, really?
Just wait till they warm back up enough. Otherwise, it's like biting into a ice cube or something on the inside.
I don't think my dentist would care too much for me to do that.
No.
Let me get it switched over so that
Okay.
they can see that.
So you can see it when I pull it out?
Yes, ma'am.
Okay, now. Sounds like a brick.
It does. Oh, my land.
And it just crumbles. Now, normally when you go to squeeze a marshmallow, it's all gooey and squishy.
Oh, yeah.
Well, this
Especially
one,
when you put it on a fire.
yeah. Well, this one broke up into a bunch of little pieces because it's so frozen right now and so hard and brittle. And how about the popsicles that you buy at the store that take how many hours for these things to freeze?
Well, for my kids, I always had to put them in overnight, or they just wouldn't freeze.
Right, that, you know, I want them now, I want them now, I want to eat them now. Well, with nitrogen, you can almost have them now because it will only take just a few seconds and this popsicle will be frozen.
Isn't that amazing? So it's no more, is it ready yet? Is it ready yet? It's like, oh, it's already ready.
So I think this one took about half a minute.
Oh, yeah.
Yep.
Now, that's about how long we've been talking. So,
Okay, so you
look,
can see
students, it's, except for that one little end down there,
up here where it wasn't in the nitrogen is still liquid.
that is amazing.
But down there it's frozen. And one last thing, which is really cool. Do you like eggs?
I actually enjoy an egg. Occasionally for my family, I'll make breakfast for dinner. So we have eggs and we have pancakes and waffles, and it's one of our favorite meals.
I'm going to do it in a smaller one so it doesn't splash me.
And so it's not frying.
It sounds like it's frying.
That's what I was going to say.
It sounds like it's bubbling away, but that's just because the egg is so much warmer than the nitrogen that it's making the nitrogen heat up and boil.
And so it won't be a fried egg, it will be a frozen
A frozen egg. And I don't know, can you get a shot of the inside of this?
We might be able to. Let me see if I can't zoom in and see if we can't. This will be our last demo, so
Right.
we should be able to get it to zoom in for us. Let's see if I can. There we go.
Okay.
Oh, that's great.
So the egg itself is actually frozen, and it looks a lot like a fried egg.
It does. It's amazing.
Oh, and it's stuck to the bottom.
Oh,
So
just like
basically,
the ones I put in my pan.
just like the ones you put in your pan. So basically, if I leave this to thaw out, it will turn back into what looks like a normal raw egg that will still need to be cooked. Because even though it looks like it's fried right now, it's not. It's still raw, so we don't want to go.
That's pretty interesting.
Yeah.
Well, Christine, we have one question.
Okay.
And yep, only one question so far. And the question is, how old do you have to be to work on rockets and to study, or what should you study in school? It's from a student named Lance in Ontario, New York, his 7th grader.
Hi, Lance. Well, basically, to be an engineer, you kind of have to have a balance of math and science and English, because you need to be able to communicate, so English is sort of still important. Those people that want to go pure technical think they can get away from having to write, but that's not kind of how it works. But basically, take as many of those type of courses that you can in high school, and then when you go on to college, there's strict curriculum set up. You can be electrical engineering, mechanical engineering, structural, aerodynamics. A lot of different types of engineers work on rockets. And actually, I started working as a college student out here back when we were doing the hybrid rocket testing, and I was actually the instrumentation and controls engineer for that project, even though I was still in college. And we actually have high school students out here working this summer who are getting a little taste of what it is to work in the rocket propulsion environment.
And that's called the INSPIRE program, students. If you're interested in doing, if I can't switch this to me, called INSPIRE. And INSPIRE is a NASA program for high school students. If you wanted to come to work at one of the 10 NASA centers, you can come to and do INSPIRE as a program, and it will give you an opportunity to work at a NASA center. But it looks like we have another question, Christine. Is what year will we be going to Mars? And this is from Jeremy in Columbus, Ohio.
Well, that's kind of up in the air right now. We have some certain milestones. We actually have rovers there now, as you know. We also have some milestones in the future out past 2020 where we would like to have a renewed presence there as well. But our missions are changing a little bit right now, and we're actually bringing more and more of the commercial companies into the NASA mission for a low Earth orbit so that we can concentrate a little bit more on going out into the beyond.
Okay. Well, let me get this question queued up, and I'm going to turn this light off over here. What is solid rocket fuel like? Is it thick or powdery or heavy or what? And this is Melissa from Boston, an 11th grader.
Hi, Melissa. Well, solid fuel comes in a few different forms. It's most like a hard rubber. If you can think about having a piece of pipe that you pour some melted rubber down inside, and it kind of, as it cools, it solidifies a little bit. So a lot of the engines that we've tested that have solid fuel inside of them, it kind of reminds me of the inside of a car tire.
Okay.
It's not quite that same thing. They have some special chemicals and different compounds inside of it, but it's basically that same consistency. And the solid fuel that's in the solid rocket boosters is a little bit more volatile compound than the hybrids, so there's some different types that they use depending on what they're trying to work with.
Okay. And we have one last question. I'll do a refresh here in a second. Must be all from one teacher's class.
Oh, this is from Tampa?
Yeah. Are there any girls that work on rockets? And I guess this is Judy, a 9th grader from Tampa.
Hi, Judy. There are girls who work on rockets. Not as many as the boys, but we're starting to become more numerous, and there's starting to be more of us. But actually, we have some pretty high-tech women out in our industry right now that are doing a lot of great work.
And boys and girls, I'd like to reiterate that NASA is still continuing to look for the brightest and the best in all fields. Engineering is not the only field out there. Sorry, Christine.
That's okay.
And however, there are hundreds of careers that you can come to work for NASA. We have a wide variety of different types of subject areas and different types of careers. If you can imagine a job, you can come to work for NASA. We astronauts and engineers are not the only people that we work with.
It's a total team effort, and without
really
everybody involved, we don't get to do what we do.
Yeah. Well, Christine, I want to thank you so much for coming and sharing
you.
your knowledge with the students today. I hope that you enjoyed Christine's presentation. Really liked all the emails. There were some really good questions today. I also want to thank Kurt, and I want to thank the DLN team for putting all this together today. But I'm Kelly Witherspoon, and this is
Christine Powell.
And I want to thank you again for coming and look forward to seeing you sometime in the future. I'm going to pass it back over to Kurt and end our program for today.
Thanks a lot, Kelly and Christine. That was great. I learned an awful lot. I love watching rockets take off, and I don't think I'll ever be able to look at them quite the same, knowing now what it takes to actually get these gigantic things up into space. Thanks so much. Again, my name is Kurt Hogan. You've been watching the Summer of Innovation coming to you from NASA Langley in Hampton, Virginia. We're here every Tuesday at 11 o'clock a.m. and Thursday at 4 o'clock p.m. Eastern Standard Time. And every day, every one of those days, we will bring you a different NASA expert from one of the 10 NASA centers around the country. Next week, we're going to be going to Johnson Space Center to teach you something about life sciences. So until then, thanks for all of your questions, and we'll see you next week. This has been Kurt Hogan for Summer of Innovation. Take care.